Good morning.
Hey Cedric, you're awake?
Yeah.
You missed my invitation to the mock interview, man. You were up at 9:15. Sorry, 9:30.
Yep, I woke up at 9:34.
Oh, okay, gotcha.
And I have to go to work in 30 minutes anyway, so.
That's not right for a high school part-time student, but okay. But also,
My boss literally asked me when are you doing classes? I'm like 9 to 1 every morning on weekdays. He's like, "Okay, I'll put you down for 9 to 1."
Oh my god.
Like,
yeah, that's the opposite of listening. But
oh yeah, and he fired the girl that had a miscarriage too.
all of that sounds very
Illegal?
Yeah, I would be sure to document all of that and also have all of your coworkers' contact information in case this comes up in the future.
Yeah, if he ever fires me, I have pictures that he sent me that I can file as sexual harassment.
Lit, you should absolutely keep track of all of that stuff. And then I'm really sad that you missed the mock interview because it sounds like you should probably be out interviewing for new jobs.
Yeah, I'm already starting to apply.
Yeah, tight. Though I mean,
Little Caesars.
Yeah. Kides sevamort martu galirma nagargar getsinzi.
I will reschedule your mock interview because it's an assignment. I'll reschedule it for Thursday because I only have 3 that day.
Michael, why is there
Okay,
two of you?
thank you.
Yeah, Michael, what?
There's 2 of you, Michael.
Where?
I think he
What?
might be signed on his laptop and on his
on my computer so
computer.
that I can see what Mr. Rob's doing in the big screen, and on my phone so I can hear him.
Wow.
Yeah.
Wow, you're so smart, Michael. Why don't you just
hey,
cast your
y'all.
phone to the TV?
So for right now, an 82-kilogram astronaut uses a spring oscillator to check his weight on the International Space Station. And when he's set in motion, the period of oscillation is 1.67 seconds. So what is the K constant for the spring? So check out your AP equation sheet, find the correct equation, manipulate it for K, and then the rest is plugging and chugging. All that we're going to do today is this is your time to work on the homework assignment because I moved the due date to it being due tonight. And if y'all have any questions in this hour, I will gladly work out and explain any and all of the homework questions that we can get to.
Cool.
Other thing is, did y'all see my update, my dump of information about the viral outbreak?
Yeah. Yeah.
Do y'all have any questions about any of that stuff? Did y'all at least see the GIF of why it is that we are separating ourselves out?
No.
Yeah, at the very least, check out that first link. Also, I don't know what else y'all are doing. What else?
Oh, this one? I saw this 2 days ago.
Oh yeah, I've seen this before. Yeah.
Yeah, that's a really clear explanation of why it is we all need to spread out and separate and stay that way for the duration.
Go to that barbecue. That's good. Yeah.
Yeah, man, it drives me crazy that people are still acting as if things are normal. And actually, a really sad thing is because idiots are like, hey, we're locked down. You want to meet up at the park and hang out? They have to shut down all the parks in the city, which is dumb because me and my wife should be able to go to the park and hang out because we're, sequestered together anyway. But they had to close them down because people are meeting up at parks and on hikes. So now we can't even go hiking together. Yeah, it's they had to put those extra rules in place because people are being stupid, but what else is new? I guess that's
pretty sure the Eden Canyon Trail is still open right now.
Pretty sure that it is either closed or it's about to be closed for the exact same reasons.
Mr. Rob.
Yeah.
Maybe.
I have a question for the AP test.
Yep.
So I know that you sent the updates, but is it basically the way the AP Gov test is going to be where instead of 3 hours, it's now only 45 minutes?
That is true of all of the AP tests. Yeah, they are all now 45
Oh.
minutes of free response only.
Okay. That's good to know.
Mr. Rob,
Yeah.
could I ask if I got the right answer?
Yes. What did you get?
All right. Is it 1,160.755 newtons per meter? Or wait, yeah. Because do you use the equation T equals 2 pi rad m over k?
You do, and I do believe that is the correct answer, yes.
All right, okay.
Congratulations.
Yeah.
Mike.
Yeah, so we'll go ahead and start off, and we'll just get through this one real quick so that we can take questions for the rest of the time. So yeah, for most of these questions, right, especially since the AP test is being butchered and chopped up into little bitty pieces, what you want to do for these oscillators, and the only oscillators they can reasonably ask you are either the spring mass or the pendulum, because those are the only equations that they give on the AP equation sheet. And so we start with the period equation. T is going to be equal to 2 pi root m over k. If you all look at your AP equation sheet, this should be on there kind of towards the bottom left. And so in this case, we were given all of the information and asked to solve for k. So from here, the rest is just a little bit of algebra to isolate k. So to get k alone, I'm going to start off by dividing both sides by 2 pi. So period divided by 2 pi is equal to the square root of m over k. And of the terms that are here, what are we trying to isolate? Yeah, we're trying to get k alone here. And so I'm going to square both sides of this equation. Square this, square that. And that gives me period divided by 2 pi, quantity squared, is equal to m over k. And now since I want k, we're going to have to go ahead and reciprocate both sides as well. And so I'm going to take both sides and flip them. So on the left, I have 2 pi over t squared is equal to k over m. And now to get k alone, I'm going to multiply both sides by the mass. Multiply both sides by the mass. And so the spring constant k must be equal to m times 2 pi over t quantity squared, which is going to be equal to 82 kilograms multiplied by 2 pi divided by the period, which is 1.67 seconds, quantity squared. And if you take this and plug and chug it, and keep in mind to put parentheses around the fraction term so that it doesn't give us back the wrong answer, we get 1231.5 for k. And what are the units here of k, of our spring constant?
Newton meters.
It's actually newtons per meter.
Oh yeah, Newton divided by.
Yeah, which, you know, there's a couple different ways that we could justify this. We could say that it's, you know, kilogram meters per second squared, or whatever thing that we want to do to try and justify that. But the easiest way to keep track of this is to think of the other equation that it comes in. Hooke's law, F is equal to negative kx. And so here, if I was to solve for k, this would tell us that F divided by x is equal to negative k. So in terms of a unitary breakdown, force is always newtons, position is always meters, and so k must have units of newtons per meter. Is this okay?
Yep. Yeah.
Cool.
Mm-hmm.
So this is like that video that we watched. Yeah, this is like that video that we watched of the guy on the spring on the International Space Station and how it oscillates to take his body weight. And it's important to keep that stuff in mind simply because in physics, there's a really big deal made about the difference between weight and mass. Mass exists no matter what, which is why we can know for sure that an 82 kilogram astronaut is an 82. I'm getting feedback, somebody's mic is open. Mute all, fixed. Okay, we can know that an astronaut's mass on the International Space Station is 82 kilograms, even though on the ISS, right, with no acceleration, what would their weight be?
A lot less.
0.
But yeah, both of those are correct. A lot less because the number is 0. Weight is mass, then multiplied by the acceleration due to gravity. So if the acceleration due to gravity is 0, the weight is 0. So even though this astronaut's weight on the International Space Station is 0, it would still interest us to know the astronaut's mass, because that is an important marker of health. Hey, nonetheless, this time is yours to wrap up the homework. So if you have any questions on the homework assignment, please hit me up. Or if you are already done with the homework, feel free to upload it on Google Classroom. And like always, you can sign out early. The only other thing that we'll be doing today is this afternoon, once I put the finishing touches on it, I'll post the pre-lab for our next laboratory assignment, which will be about determining the damping factor for 2 different oscillatory systems. That pre-lab will go up, and then tomorrow for class, we'll start off by going over the questions. So they won't be due or anything. We'll just like go over the answers together. And then we'll do the first day of the lab. I'm expecting it'll probably take 2 days to do all the parts of it. And then, like I said, since I'll be taking the data with those Vernier tablets, once I have the data exported from them and put on Excel sheets, I'll upload that. And we'll talk about analyzing the data from those sheets together.
Okay.
Mr. Robinson.
Mm-hmm.
Okay, wait, is this going on YouTube or no?
This one maybe no, just because it's workshop stuff, though I still need to upload the one from yesterday. Why do you ask?
Because I was going to ask a burning political question.
I'll probably pass unless it's just something like straightforward and factual. Like, what's the question?
What are your thoughts on the Democrats declining the first round of voting for the stimulus package that Trump's trying to employ?
You know, that's a good question. Based on, and it's not a thing that I put a super big amount of research into.
Do you need a rundown of the basic reasons of why they said no?
No, I saw it in, let me find a news source I like. Give me 1 second. I can understand how a stimulus offer would be phrased in such a way that it overwhelmingly benefits the rich and corporations over the people who it's supposed to help. I could understand why an initial offer would be rejected, but with the current breakdown of the House and Senate, I have no idea what a compromise looks like between those 2 bodies.
Mm-hmm.
I also don't know what the rules are going to be about voting, considering a bunch of people in those bodies are probably sick.
Yeah.
Considering Rand Paul has coronavirus, and for whatever reason, the Senate has a publicly open bowl of jelly beans. They're just like, hey, can grab a handful of jelly beans before you do your governing, homies. So like, if that dude put his hand in the jelly bean bowl and then other people came up and took some senatorial jelly beans, there could be more than just one senator with COVID.
Makes sense.
Mr. Rob, did you hear that Chuck Norris has it?
That's a meme.
I'm pretty sure he actually got it.
No, I think that's a meme.
I don't know.
And I would need really like rock solid evidence to think otherwise.
Mr. Rob, could I ask you a homework question?
Yeah, please. Thank God. Yeah, what's up?
Number 15 on the problems and exercises.
Okay. So a 0.500 kilogram mass suspended from a spring oscillates with a period of 15 seconds. How much mass must be added to the object to change the period to 2 seconds?
Yeah.
Okay. So this is a 2-factor calculation. Based on that initial information that they're giving us, a 0.5 kilogram mass suspended from a spring oscillates with a period of 1.5 seconds. What does that information allow you to calculate? It's actually the same as the warm-up.
Okay, so we use the same equation, T equals 2 pi rad M over K.
Yeah.
And it tells Oh.
So question number
Can you
15.
just like 1.5 like equals 2 pi over, you know?
Right, but
Or-
as always, we never want to just plug in numbers before we start doing algebraic manipulations. We
Oh,
want
yeah,
to
that's
solve
true.
for the thing that we want to solve for first, then plug
Yep.
and chug. So
Yep.
you'll notice here that they gave us period, they gave us mass, and that actually gives us enough information to then solve for the spring constant K, right?
Okay. Yeah.
So it's the exact same manipulation as we did in the warm-up, so I'm just going to jump to that line. So that is to say that the spring constant K is going to be equal to m times 2 pi over t squared, right?
Yeah.
Plug and chug with the information from the question, so that will tell us what the spring constant is. So that's going to be equal to 0.500 kilogram, 2 pi divided by a period of 1.5 seconds, then squared. And this is enough to tell us that the spring constant of this theoretical spring in the laboratory is 2 pi divided by 1.5. Square that times 0.5. The spring constant is 8.77 newtons per meter.
All right.
And with that information in hand, then you can go back, take this, remanipulate it again, except this time you'll solve it for m. So that'll be t divided by 2 pi is equal to root m over k. Square both sides again, and that tells us that m will be equal to t over 2 pi squared, then multiplied by k. And now that we know k, and we know that we want to change the period to 2 seconds, that will let us calculate what the mass would have to be changed to. So the new mass would have to be equal to 2 seconds divided by 2 pi squared, then multiplied by k, which we calculated to be 8.77 newtons per meter in the previous question. And so the mass is going to be equal to 0.889 kilograms. So what's the answer to the question?
You subtract the.
Yeah, you have to subtract these two
subtract
masses
the
because the question asks how much would you have to add. So the answer is we would have to add an additional mass of 0.389 kilogram. And then that would retune the spring to give us our desired period.
Okay. All right. Thank you.
Yep.
Can you also do number 3 for problems and exercises?
One type of BB gun uses a spring-driven plunger to blow 1 BB from its barrel. Calculate the force constant of a plunger spring if you must compress it 0.15 meters to drive it the 0.5 kilogram plunger to a top speed of 20 meters per second. What force must be exerted to compress the spring? So good question. Item number 3. So there's a couple different ways that we could do this. And I'm going to choose to use conservation of energy, just because I think that that is probably the coolest formulation that will give us the correct answer in this case. And here's how I know that like conservation of energy will be a good approach. Conservation of energy stuff tends to be time independent. And here they're not giving us a time, they're not asking us about a time. And so what I can say is that the potential energy in the spring will become kinetic energy of the plunger, right? Like what this is saying is that much like the plunger on a pinball table, you take it, you pull it back, you let it go.
Mm-hmm.
So we're taking the spring, we're crushing it down, and then when we let it go, it's going to drive some kind of plunger that's inside of it. And so what's the potential energy of a spring?
Isn't it half kx squared?
That's 1/2 kx squared. And then all of this potential energy stored up in the spring is going to become kinetic energy of the plunger. And what's the kinetic energy statement?
MV squared? Or
1/2
1/2 MV squared.
Yep. And of these terms, right, what are we being asked to solve for first?
The K.
Yeah, we're being asked to solve for K first. So the first thing I'll do is I'll multiply both sides by 2, which instantly gets rid of these 1/2. And then after I've gotten rid of those 1/2, I'm going to divide both sides by x squared. So the spring constant K is equal to mv squared divided by x squared. And so the rest will just be plugging in those two parts. So the mass of the plunger is 0.05 kilogram. We want to get it up to 20 meters per second of velocity, its top speed, and that'll get squared because of this formulation. And then we'll divide that by the distance over which it gets compressed, 0.150 meters quantity squared. And this calculation will give us our correct answer.
Okay. Thank you.
Yeah, you're welcome. Does that setup make sense?
Yep.
Cool.
What would be the other way to solve it?
I can give you a completely different way to solve it, and that's actually a really good question. Give me 1 second.
Okay.
So just so you know, you get a bunch of 8s.
Okay.
Here's the other way that you can solve it, and like I said, the thing that led me to go for the conservation of energy is the fact that conservation of energy is a stand-in for our time-independent equations of motion. Because notice that this statement, this is time-independent. This is just saying, I have this much energy available. What is the max speed that I will achieve with this? But this answer doesn't give us a function of time. So the other way that you could do this without using conservation of energy is you could say, well, I know that the equation for a spring is F is equal to negative kx. I have this part, right?
Mm-hmm.
So over here on the right, this is my second version of this solution, a big old or at the top. And so what can we plug in for F? What does Newton's second law tell us?
F equals MA.
Yeah, F equals ma. So mass multiplied by acceleration is equal to negative kx. I'm going to do this up and solve for k. So this is to say that k has to be equal to negative ma over x, right?
Mm-hmm.
So this will also give us the correct answer, except the problem gives us m and the problem gives us x, but what does it not give us?
Don't know.
It doesn't give us acceleration.
Oh, okay, yeah.
It does give us the final velocity, but it doesn't give us the final acceleration. However, luckily, there's enough information to solve for that acceleration. Did this problem give us time, or did they ask us about time?
Did they give us?
Yeah, did they give information about time, or did they ask information about time?
No.
No. So that's how we know that the other thing that we're going to need to manipulate here is the time-independent equation of motion. V squared is equal to V naught squared plus 2ax. Now, we're going to assume that the plunger accelerates from rest. Yeah, which it does. So this initial velocity here, that will be 0. And so I'm going to solve this guy out for acceleration. And so this is going to tell me that v squared divided by 2x is equal to a, where v is the final velocity of the plunger and x is the distance over which the plunger can accelerate.
Okay.
And now I'm going to take this definition for a and I'm going to plug it in here, and we're going to see something fairly cool happen. So k will be equal to negative m. Now I'm going to make my substitution for a. V squared over 2x, then divided by x. Is this okay?
Yeah.
Yeah. And you'll notice that this right here simplifies down to mv squared over 2x squared with a negative out front. Oh wait, that's weird. Wait a minute. That should work out exactly the same as the previous answer, except this one's different by a factor of 2. That's weird. That shouldn't happen. V squared divided by 2x is equal to a. That's good. mv squared over 2x
Yeah.
squared. Anybody spot the mistake? Conservation of energy, 1/2 kx squared is equal to 1/2 mv squared. Both sides cancel out the 2, so this is correct.
Yeah. Mm, that's weird. What?
Yeah, they shouldn't be different by a factor of 2. Both of these approaches should give the exact same answer. I'm sure I made some silly mistake in my setup. Give me a little bit to think about it, and I'll get back to you.
Okay.
Huh. This is weird. Yeah, there's a... Huh. I am deeply bothered by this solution. Hmm.
I mean, everything looks right.
Yeah, but you can't have 2 different solutions that disagree with each other. I
Yeah.
thought these were going to converge on the same thing. I don't understand why they're different by a factor of 2.
Mm.
Hmm. Yeah. So this answer here, the first one I did, this matches perfectly. So there's something wrong with my logic here.
Okay.
So force is equal to negative kx. That's true. That's just Hooke's law. Force equals ma. This is just Newton's second law. Ma is equal to negative kx. So k is equal to negative ma over x. And then if we're trying to figure out acceleration, we know the final velocity of the thing. We know the distance over which it's accelerating. So this A right here should be the acceleration of the plunger. This is fine, and the logic is that it would accelerate over the same length that the spring is compressed, because if you take a spring and compress it 10 centimeters, it's going to jut out that same 10 centimeters.
Yep.
And then you should be able to take that, plug it back in. And have it give you back K. Oh, I know what the problem is. Yeah, so this formulation is wrong. Yeah, this actually can't work out over here on the right, and it's for a really picky reason. Yeah, so this is actually, these two steps are incorrect. You can only do it by this method on the left, but why this is wrong is actually pretty subtle. Does anybody want to try and offer an answer as to why this may be wrong?
Like why we can't use acceleration.
Yeah, why this doesn't actually, this formulation right here in particular can't work out in this case. There's a requirement here that we're not meeting.
Don't know.
Yeah, so this equation right here, it actually only works under constant accelerations. So like when we use this equation normally, we're talking about like the constant acceleration of gravity or whatever. Like, oh, you just have 9.8 meters per second squared unchanging. But does a spring apply a constant force?
No.
No, this equation says that the force gets smaller as the spring expands. So this acceleration right here in this line is being written as a function of x. And because of this non-constant acceleration, this relationship can't be used.
Okay.
Mr. Rob.
Yep.
I gotta head out.
Okay, have a good shift.
I'll try.
Yeah, or try. And that's why these two are giving us different solutions.
Alright,
This
Okay.
one over here on the right is invalid because the kinematic equations only work under constant acceleration, and it's a small subtle thing. But right here, this is saying that the acceleration changes.
Okay. Thank you.
Yeah, good. Actually, really good question. Yeah, the best approach there is energies.
The energies, okay.
Mr. Rob.
Yep.
For number 17, I understand that for B, you just use the T equals 2 pi rad m over K. But then for C, I don't know how to relate it to velocity.
Which page is it?
Which page?
Which page in the book? Just because I scrolled to the end of the book.
I'm on the online one, so let me try to find it.
It'll just say on the corner of the page like a normal book does.
It's not showing it.
It's okay. Give me 1 second. I just gotta scroll back over to it.
All right.
Okay, view online, chapter 16. Problems and exercises. And you said question 17?
Yeah.
So suppose you attach an object with mass m to a vertical spring originally at rest and let it bounce up and down. You release the object with rest or from rest with the spring's original rest length. Show that the spring exerts an upward force of 2 mg on the object at its lowest point. If the spring has a force constant of 10.0 newtons per meter and a 0.25 kilogram mass is set in motion as described, find the amplitude of the oscillations, find the maximum velocity. Is that it?
Yeah.
So which part was your question on?
Well, I guess we could just start from A because like that's a little confusing. An upward force.
Oh, yeah, I got you. Yeah. So why is it that at the bottom position of a spring, it would have to exert double the weight in order to pull you back up?
Is it because you have to overcome the downwards gravity and then
Yeah, you
That-
have the right idea. Give me 1 second. I'm out of notebook paper. I'm just going to grab
Oh,
some more paper.
All right.
Yeah, so I think I actually really like that question. It's worth thinking about. So this is question number 17, part A. So you have an object bobbing up and down on a spring, and let's say that this right here is the equilibrium position, right? And so the answer as to why at the bottom it would be 2 mg worth of force coming from the spring, I think is fairly interesting. So right here in the middle, right, at our equilibrium position, what should the sum of the forces be equal to? What is the definition of equilibrium?
Sum of forces is 0.
Yeah, so right here, the sum of the forces would be 0. So right here, this is going to tell us that downwards we have mg, and then upwards we have the force due to the spring, negative kx. But this is equal right now in magnitude to negative mg, so that mg plus negative mg adds up to 0. The argument for why this acceleration at the bottom would have to be double is the fact that we expect symmetry coming out of this system. So at the very top, right, the spring would be doing nothing, mostly because we're going to reach the top, and then what's going to pull the block back down?
Gravity.
Yeah, gravity. So right here at the top, we would expect this to be at 0 extension, so there is no kx at all in the upwards direction. And then downwards, we just have an mg, which is to say that downwards, our acceleration is equal to g. So at the bottom, right, if the acceleration at the top is g, at the bottom here, we expect the acceleration back up to be g as well. However, to achieve this, the spring has to be doing double the amount of force as gravity, simply because then at the bottom, mg doesn't change, right? But upwards, the spring will be extended twice as far as it is even in this position. So this is 0, this is x. Now we're extended out to 2x. So this will have to be a force equal to negative 2 kx, which is going to be equal to negative 2 mg. So that when we add these two together, the grand total is an upwards force of mg. So here at the bottom part, the sum of the forces is going to be equal to 2 mg coming from the spring minus mg coming from, the earth, so that the sum of the forces is mg, but upwards.
Okay.
So that's it. Lots of fancy free body diagram stuff and logic. Also for this question, B is straightforward. That's just asking you to plug and chug. And for the last part, C, find the maximum velocity. That again is a pretty straightforward calculation. For calculating maximum velocities, it's conservation of energy. So 1/2 kx squared, which is the potential energy stored up in that spring, is equal to 1/2 mv squared. And again, if you want to know the maximum velocity achieved by this block, we're going to hit both of these 1/2s with a 2. Kx squared divided by m, then square rooted will give us back v.
Okay.
Really good question.
Mr. Rob,
Yep.
for number 13, do we use the same equation we used in the warm-up?
Yes. Yes.
Okay.
Same thing. You're solving for k based
For
on the given
K.
information.
Okay.
Wait, Mr. Rob,
Yep.
for that number 17,
Yeah.
I see all the variables to find C except X. Well, what would my displacement be?
Oh, so the displacement is going to be the amplitude. So look there in that
Okay.
in
Oh.
part B, right? They're telling you what the spring constant K is and what the mass of the object is.
Mhm.
So what X has to be is if we're hanging a weight from a spring, it's going to kind of sit down at a natural length. Like that's what the logic is behind a spring scale. The heavier an object is, the further it will stretch out a given spring. So the weight is just, the force is just the weight. So mg is equal to negative kx. And if you solve for that x, this will tell you what the natural amplitude of
Morning.
oscillation is.
Okay.
Is that okay?
Yeah, thank you.
Mm-hmm.
Good morning,
Hello?
Alan. Sorry, Mr. Robinson. I got a call from my work.
It's fine.
Mr. Rob,
Yep.
do you mind checking what the changes to the AP Calculus test are, if they're out?
Sure. Yeah.
All right. Thank you.
Yeah. I can interpret any of that stuff for y'all.
Mr.
So,
Robinson,
yes.
I'm gonna head out.
Get the homework out.
All right, I'm pretty much done, so I'll just upload it like around 2.
Okay.
All right, later, Mr. Robinson. Have a nice rest of your day.
See you tomorrow.
See you tomorrow.
And just a quick reminder for y'all today from 2 to 2:45 p.m. Eastern, which I guess is 5 to 5:45 here, there will be the first part of the College Board's official AP Calculus review, in case you want to look at how to model different situations with differential equations, which is what we talked about with the springs, right? Where the homie was equal to its own second derivative.
Oh, yeah.
Sorry, I'm looking for the adjustment. Wait, I'm being dumb. I can't find the part where it said which topics are being removed. I might have to go bug my wife. No. Yeah, for some reason my brain is smooth and I can't find the correct page for them talking about which things are not going to be on the test.
All right, that's fine.
Unless they already changed that rule too, and instead they're going to cover everything.
Yeah, I just wanted to know if they would cut any of the content off.
Yeah, I mean, I could be wrong. It looks like they changed it since the last time I read through this information.
Oh, okay.
Yeah, I'll be right back. Let me go talk to my wife real quick about the page where it said which units were going to be removed.
All right, thanks.
Yeah, I'll be right back.
Thanks, Michael. Why is everyone so quiet? Oh
And now I made him go up to his wife.
Michael John Ray Jr.
Yeah, can people ask questions?
Yeah, what the hell? It doesn't mean Michael.
Okay.
So if I leave now, he won't know I left. Should I do it?
No. I'm gonna ask 19.
Alex, ask a question.
Yeah.
Bro, is it Monday scheduled today?
No.
No.
Not sleep.
Oh, my floor is
Guys, we might not see each other again. Oh. Fuck.
Oh,
Sucks, man.
I have corona, guys.
Stop. Probably.
I haven't heard Alex. Is Alex here?
Yeah, I think he's
He
sleeping.
definitely fell asleep or something. For sure.
Alex.
Oh, I was looking at the wrong page. Okay, so it should be calculus. So calculus AB will cover units 1 through 7. It will not cover unit 8.
All right. Do you know what unit 8 is or no?
Yeah. I'm gonna screen share my window in a second. Give me 1 second here.
All right.
Okay. I'll post both of these links when I'm done. So let me share Chrome. Share. Okay, do you see Chrome?
Yeah.
So this is the link that you want, AP updates for schools impacted by coronavirus. So we scroll down to Calculus AB, and in the table it has the name of the subject. Exam questions will only cover these topics. Exam questions will not cover these topics. And they'll get around to this later for everybody. What types of questions will be asked? So for Calculus AB, right here, it will cover units 1 through 7, but it will not cover unit 8, which is the only one being omitted. So if we go over to the course at a glance for AP Calculus, it's going to cover limits, it's going to cover differentiation, it's going to cover differentiation like the fancier techniques, it's going to cover contextual applications of derivatives, analytical applications of derivatives. It's still going to cover integration, it's still going to cover basic differential equations, but it will not cover applications of integration. So it will not cover area between curves. It will not cover the physics stuff like position, velocity, acceleration as integrals. It will not cover volume calculations either. It won't do the disk method or the washer method, even though I spent a bunch of time beating that into my own calculus class.
Jeez.
So yeah, this stuff here in column 8 is what it won't cover.
Okay. All right. Thank you.
Yeah, it's good stuff. Yeah, it's a good question. Anyway, AP physicists, y'all have a nice day, and I'll see you tomorrow. Look for that pre-lab, though, like I said, it probably won't go up until a little bit after lunch because I got to put finishing touches on it. And I don't really expect you to do it on your own. We'll do it together tomorrow when we start class, right? And then after that, I will do a thing where I take this document cam down and I'll point it in a direction at the lab equipment that we have to work with. And we will do the lab together. And then after the lab is done, I'll post the data online and we can do the data analysis together in Excel as well. I just want to make sure that everybody gets it. Are there any questions there?
Nope.
Oh, also, did you see my ghetto sound baffling? Yeah, man, gotta stop that echo by any means necessary. Anyway, y'all have a nice day, and I'll see you tomorrow.
Let's see.
That's good. Thank you.
Yep.